comes down to peaker plants. They are the culprit. And here's what really adds insult to injury. Even though they're contributing half of our carbon footprint, they're only delivering 5% of the power that's actually used.
It's like we are trying to power all of our energy systems, whether they're used for AI, data centers, whatever, as if it's like a Ford Model T car, and we're trying to power, trying to be a spaceship.
If I had a glove of Thanos and I could snap my fingers and magically connect all of those to our AC grid today,
right,
it would melt down the grid because it couldn't keep up with an extra 3 terawatts of power.
Hello and welcome back to Swift Start Go, the show where we talk all things AI, creativity, and the future of work. And today we have a killer episode for you. Okay, I hope you're really excited. On this show, as you know, we focus on translating AI jargon and hype for creatives so that they can succeed in an AI economy. Now, this episode is going to be a little different, but I think you guys are all going to find it absolutely fascinating. Today, we're going to be talking all about AI, energy, and climate with a friend of mine who's doing incredible work fighting the energy crisis, or helping the energy crisis. How do we, I guess, help fighting it? Yeah.
Yeah, just trying to make it better.
Just trying
as quickly as
we're
possible.
We're just doing our best over here, right? All right. Our guest today is Sam Goff, the founder and CEO of Crucible Energy. He has spent over 30 years of his career in mission-critical and real-time data, including most recently at Hewlett-Packard Enterprise and an AI startup focused on automated software quality, and over 10 years in superconductors and grid architecture. As you may already know, AI is incredibly energy hungry. It requires a massive amount of resources to power and cool data centers, and can be as large as Manhattan. Building out these systems is dominating our economy. Estimates show that investment in AI-related infrastructure now accounts for roughly 4% of U.S. GDP, but that small share has been responsible for more than 90% of GDP growth in the first half of 2025. Wow. This is an unbelievable amount of investment and has resulted in an incredible strain on utilities and energy grids. Sam and his team at Crucible Energy are addressing this by tackling some of the biggest problems in our energy grids and data centers. Today, we're going to be discussing what are the biggest problems in the energy space and how AI is changing that landscape. Sam, welcome to the show. You made it.
Thank you. Yeah, it was fun drive, but I'm so glad I made it.
Yeah, absolutely. I'm so glad that you're here. We're going to have the best time today. I would love to start just by zooming out and getting into some big picture stuff. Does that sound good?
Bring it on.
All right, amazing. So our energy grid here in the US is dated and struggling with these massive increases that we have seen in the last decade, right? It's not just this new AI revolution, it's everything for the last 100 or so years, right? Yeah. So I'm curious, how did we get here? And what are some of the biggest problems that we've seen so far?
So I should probably point out that it's not just in the US. This is the problems with the grid are fundamental to the design of the grid. And these decisions were made 100 years ago or longer. And at the time, it made sense because that's all the technology that they had. But now that we're trying to grow our grid at more than 5% per year,
right,
the AC grid cannot keep up with that rate of expansion. That's how we got here. Is we have engineers 100 years ago doing the best they could with what they had, and they didn't have real-time data. They didn't have fiber optics. They didn't have blockchain integrated sensors. They didn't have any of that. So that's how we got here. And the problem is because it's the innovator's dilemma. You have a system and an ecosystem that has invested so heavily in an outmoded technology, the incentives are misaligned. Right. And so you have some people rowing the boat that way, and you have other people rowing the boat in a different direction, and they're not getting very far as a result. So I think of it in terms of perverse incentives or misaligned incentives versus how can we basically align those incentives so it becomes more of a win-win-win for everybody?
Yeah, that makes a lot of sense.
The biggest problem that I see is the grid is slow to expand, and it's also not nearly reliable enough. If you say, "Oh well, we have 99.9% reliability," do the math. That's hours, and if you have an outage at the wrong time, that can actually cause people to lose millions or even billions of dollars worth of product that's in the process of being manufactured.
Yeah.
If it's at a hospital that loses power,
people can lose their lives if they don't have the energy needed to keep certain machines on.
Yeah. So there's a cost of not having 100% reliable or resilient power. And that is over $500 billion per year worldwide. And over 100,000 people die as a result of, let's say, elevated carbon monoxide.
Yep.
Because they have to turn on a gas generator and they don't have proper ventilation. And so every time there's an outage, you can watch as the death rate spikes due to, different side effects that can be traced directly to the outage.
Yeah.
So this has a very real impact on people's lives, their quality of their lives. And it's part of the reason why our prices for our electricity keep on skyrocketing. I think they went up 1.5 times in the last year.
I think there are people in a few states, but I was reading specifically about Virginia, where their energy costs have been going up like crazy because of AI. These data centers and all of the stuff that's combining onto the energy grid. I know we got it. That's our next question.
I was going to say, let's put the blame where it deserves, because the data centers themselves aren't the problem. It's that the grid can't grow quickly enough to keep up with it.
Okay.
And so to put this into perspective, the DOE did a study back in 2023, and they figured out, okay, so how much is the grid growing, and how much do we need to expand the grid in order to catch up to this demand and eliminate the congestion? And the answer is 47,000 terawatt hours is the gap that we need to add. Put another way, it needs to be expanded no less than 57% above and beyond what it is right now. And that's just to cover until 5 years from now, 2030. So the problem is with AC grid, it can only grow, it can only expand at a very limited rate. And reactive power, which is a thing in the world of AC, means that you have all kinds of complexities that you have to worry about, that if you're using, let's say, DC or other modern technologies, you just don't have to worry about it. And so it's much easier for us to reason about things kind of the way that people reason about networks and computing and building the internet. You can borrow a lot of those ideas and apply it to the power system, and all of a sudden 99% of those nightmares go away. Those headaches go away. So,
well, you've jumped on this a little bit, but I want to rewind slightly because one of the biggest questions that I get specifically about AI and energy usage is, why does AI use so much energy and also water? I know a lot of that has to do with cooling systems, in addition to like the larger scale grid questions, statements, ideas, concepts. What's the word? Oh boy. but you get what I mean. And so can you break down why this entire category, whether it's AI, data centers, the grid, is considered so energy and water intensive, and why we need to solve this issue? Can you just like break it down to a few blocks for us?
Yeah, really simple. The AC grid is it's
and by AC you don't mean air conditioning, you mean
alternating current.
Yes, which is typically how all of us get our power nowadays. So if you're looking at power lines across the country, those are typically AC.
Yes. 99% of the power lines that you see above
up in the air,
towers, over the head, they're called OTH. Those power lines, 99% of them around the world are AC.
Yes.
Alternating current, in specifically 3-phase AC. Because it's a more efficient way to carry power but that's all relative. It's
Yeah.
you still in the U.S. you lose about 10% of your power simply by moving it through copper or aluminum, and it's not a perfect conductor.
Yeah.
So that 10% that's lost, it's lost as heat, and it actually heats up the cables, which is why you have to keep them apart from each other. That plus there's electromagnetic interference, EMI,
Yeah.
electromagnetic interference. And what happens is you need to keep the cables apart so that they don't create induction currents in anything metal around them.
So is that why when you see power lines, there's like the pole in the middle, and then there's like the cross right here, and then there's one line here, one line here, one line here. It's keeping them separated. Oh, gotcha.
Yeah, you
Okay.
gotta keep it separated.
Yeah.
So yeah, that's why it's not feasible to expand the grid as quickly as we'd like to.
Yeah.
Because those towers at the side of a road, if you've got two 500 kilovolt towers, it basically carries about 2 gigawatts,
Right.
and it occupies a 100-meter right-of-way. Translate that to 328 feet, give or take. If you move over to, you raise your voltage, then you can get away with just a single tower that carries 2 gigawatts. And that's only, and I put air quotes around only,
Right.
85 meters or 278 feet.
So kind of what you are describing here is our energy systems are really slow, they're inefficient, and it's really old technology. It's technology that's 100 years old. So when I hear this, it kind of sounds like we are trying to power all of our energy systems, whether they're used for AI, data centers, whatever, as if it's like a Ford Model T car, and we're trying to power trying to be a spaceship. Is that kind of what I'm hearing?
Yeah. I mean,
Yeah.
these lines were, some of them were built in the 70s and 80s,
Right.
and they haven't really been upgraded. And now there are some glimmers of hope on the horizon, but generally speaking, you can't make more land.
Yeah.
I mean, the Chinese are trying to in the middle of the ocean, in the middle of the Pacific,
That's true. They have all their islands, huh?
but they're manufacturing islands. But in general, it's really hard to manufacture more real estate.
Right.
And so that right of way describes how much space at the side of a highway or a railway you have to set aside in order to be able to move that much power.
Yeah.
And it's very linear, whether you're talking about high voltage alternating current or HVAC, or high voltage direct current, which is HVDC. It doesn't matter. If you're working with high voltage AC or DC, you have a linear multiplier, meaning if you have, let's say, 2 gigawatts of power, but you really need, let's say, 10 or 20 gigawatts of power, you have to take that 100 meter right of way and multiply it by 5 or 10.
Yeah.
And we don't have, let's say, 1,500 meters set aside at the side of every roadway for us to be able to do 5x or 10x.
Yeah.
All of those. You know what I mean?
Yeah. So that sounds like this is one portion of the issue, is again.
Yep, that's one aspect of it. The other aspect of it is because they're adding it so quickly, there's the demand for AI has exploded, right?
Right.
And because they're and the demand of AI chips in particular is very grueling.
Yep.
Because they're kind of the evil twin to sustainable energy generation.
Right.
Because on the generation side, the problem with the power grid is it's not designed to handle variable production. They're used to what's called base load generation. They create a coal-fired plant, or these days it might be a natural gas plant.
Right.
But the point is, it's always running at the same speed. It's not intended to be cranked up or down.
But that's not how, like, if you're thinking about who uses AI and when, people use them at certain times of the day or certain times of the year, or,
Right.
It
gets even worse than that, though.
Yeah.
It's not just the end user who's typing in, a question into ChatGPT. It's how those models are actually trained, and then how inference is occupied, which is every time you see a model that says thinking, that's called inference. It's really search applied to the AI space. But the point is that when you're training a model or when you're fine tuning a model, you can have, let's say it's a gigawatt data center, you can have swings within about a millisecond. You can have swings up or down in the hundreds of megawatts range.
Yeah.
And that's the other thing. The grid is not designed to have a system that is normally just, chugging along, and then, oh, I've decided I need 10 times more power from you now. Oh, it's a millisecond later. I've changed my mind. I only want, 1/10 as much power.
Right.
And to be able to make those massive swings in the rate of power delivery, or the amount of power that's being delivered within, like, we're talking milliseconds, the AC grid was never designed to do that. And it's very expensive to try and solve it using that technology.
Okay. So it sounds like we have a few things. So first is physically transporting the energy from place to place is challenging.
Yeah.
Then we have when you are training these LLMs, the model training, you have significant spikes and significant decreases of how much energy you need at any given moment, which makes a lot of sense. And so if you can't get the amount of energy when you need it, what happens? Just the things break down or things slow down? Or
if you can't get the amount of energy that you need when you need it, either things, you might see the lights flicker. You might see components actually fail.
Right.
Because they're designed to always operate within a Goldilocks zone.
Okay.
Right? It's got to be within certain tolerances. And if you have way too much power or way too little power, you have things that break. And these things that break are very expensive. I mean, an entire substation might be $250 million.
Wow.
Or more. Okay? So if you have components failing that are millions of dollars, it affects everybody's electrical price, right? What they pay for their energy bill. There's one other piece of the puzzle, though, that we haven't touched on, which is part of the reason why data centers are so energy intensive is because they generate a tremendous amount of waste heat.
So much heat.
So we were talking about how the power transmission system in different parts of the world, it might lose 10% in the US due to, they're called resistive losses or ohmic losses. It's because copper isn't a perfect conductor. Right. If you go to the EU, that actually goes up to about 16% resistive losses. If you go to developing regions in the world where they actually have people stealing the power by running coils around the wires and using induction, they're able to steal the power, and it's so variable they can't even keep track. They're losing over 30% of their power simply because it's antiquated and there's no way to track where that power is going.
Right.
Which is one of the things
because
solved.
we have dated systems where you can't track anything because they were made 100 years ago, or maybe in the 70s. It's like the New York City subway. Nobody knows where the subway is.
Yeah. That's exactly it.
Except for on the the L. There's one line that goes from Manhattan to Brooklyn where it's like the only one that has any sort of digital tracking, or at least that was the case 6 years ago when I was taking the subway regularly.
It's hilarious.
In the subway systems in New York, the way they track the subways is from tech that was invented in the 1940s, where the trains have to like physically pass something and like hit a piece of metal, and then the metal goes, ding, it's here. And then in some room somewhere, I don't know where it is, maybe it's in Grand Central or something, a little light will go off saying, oh, this train is in this location now. And that's how we track the subways. Or at least that's how I understand it. Perhaps I'm wrong. But okay. And so, and I've also heard that one of the big issues with data centers, and I know this is not necessarily your area of expertise, but if we could touch, you mentioned they get really hot, the cooling systems. The cooling systems require a lot of energy as well. Right. And I would assume that they go through the same swings as like the basic model training stuff, maybe?
I mean, there's a bit more thermal inertia. And actually, this is something that I've solved. This is something that I'm working on solving the entire.
Sam, you've solved everything.
No, I haven't. But this was one of the big ones. I'm like, look, this is a pain point. Somebody needs to solve it. Oh yeah, I've got this technology. I can basically repurpose it to make data centers that don't produce nearly as much waste heat. So 40% of the energy bill for a data center, a typical data center, with what's called a PUE of 1.4. It's a description of how much power do you need to put in order to get the amount of useful AI compute out, right? And so some of the more efficient data centers in the world are a PUE of 1.4, which means you have to put in, let's say, 1.4 gigawatts in order to get 1 gigawatt of compute back. So you're basically expending 40%. Some of that is on heat, but then you expend that 40% cooling off that waste heat so that you don't have server racks melting down.
Yeah.
So what I figured out is if you can prevent the waste heat from being generated using superconductive power distribution units and bus bars, and then you switch your networking from copper to fiber optic and an optical waveguide, all of a sudden you have a PUE closer to 1.05. So you only need to put in 5% overhead in order to be able to get your data. And because you're not generating waste heat in the first place, then you don't have to spend the money and energy cooling it off.
Right.
And so normally people like you and I would say, oh, well, yeah, I'm saving money. Cool. That's awesome. My power bill is going to go down.
Yeah.
AI data center operators would look at that and go, oh, I have, if I've got 1.4 gigawatts of power, that means if I have a PUE of 1.05, I can get 35% more, or whatever the calculation would be.
Yeah.
I can get a heck of a lot more compute for the same amount of power.
Right.
So they think of it as, oh, more power. And then that means that they don't have to build as many data centers as quickly in order to be able to grow the compute, all other things being equal. So what it means is you can do a lot more with a lot less.
Yeah.
Because you're solving the fundamental root cause of the inefficiency in the first place. And I'm literally partnering with hyperscalers right now to build these data centers that I'm talking about.
Yeah.
So,
oh my God, it's too cool. It's too cool.
Yeah.
And we'll be right back with a note from one of our sponsors. Some connections take a minute, but on the day of your wedding, you need the right buffer. And who better to be the official buffer than Reverend Shabazz? Don't settle for anything less than the real deal. An officiant who wants your wedding to go your way, as it should be on your special day. Choose Getting Hitched with Shabazz and load no longer. Link in the description down below. And we're back. And Sam, listen, I got to ask you more questions about problems in our energy grid. Are you ready?
bring it on.
Well, one of the biggest issues that we discussed earlier this week when we were prepping for this meeting was talking about outages and quality issues when it comes to these grids, data centers, et cetera.
Yeah.
So can you explain what these are, I think specifically for the energy grid, and why they happen?
Yeah. So I've mentioned this before. Outages and power quality issues amount to a cost, a financial cost of about $500 billion every year. I think it's about 150 billion specifically in the U.S. We have it fairly easy here, but it's still it's a very expensive problem, and because when you have blackouts, brownouts, transients, things like this, spikes, voltage spikes.
Yep.
Let's say you have a lightning strike. You have a failure of a component because it can't handle that level of current going through it. So these are the types of things where part of the problem is the original design of the alternating current or AC grid is based on what's called a radial network. And if you wanted to design a network so that it was more likely to fail,
that would be the way to do it.
That is absolutely the ideal design because there are so many single points of failure. And what that means is you're putting all your eggs in one basket.
Yeah. So if we're going to visualize a radial network, and we're actually going to have this on the screen, but for anybody who's listening and can't see what's on the screen, can you picture a tree branch and picture like a longer branch where maybe in one of the places where like it breaks off and there's like a mini branch on a bigger branch, there's like a little bit of a power station. And then one of the ones goes further, one of the ones goes over. Maybe they break off again and they go in different directions.
Exactly.
So that's how I would think about, what did we just call them? Radial?
Yeah.
Radial
It's
network.
a radial network design.
And so that's how most power systems here, or all power systems here in the US basically work.
It describes the AC, or alternating current power system, that most places have built out. We're talking 99% of the world's power system.
Right.
It really is described as a combination of transmission and distribution, or T&D is what they call it for short. But transmission, and that's the other part of the problem with the power grid, is it evolved with two different siloed systems. Long distance transmission operates with one set of technology and voltages and equipment and stuff like that. And then distribution is a lower voltage, and it's got a different ecosystem there.
Right.
And so then you have additional complexity because you're trying to move power across two different systems. And ultimately that has created all kinds of baggage and additional expense and complexity and just,
Yeah. And it's the type of thing where, like, on these branches, if you have a lightning strike, if you have a tree hit a single wire, it can make it so that entire neighborhoods or businesses or regions have an outage. Yeah.
So I think of cascade failures and situations where there's a human in the loop,
Right.
or there's let's say there's a hydropower in Ohio. I think this happened in Ohio, and it created a knock-on effect. It created a chain reaction going from Ohio all the way to the eastern seaboard, and it brought down all of the power in New York City and the Northeast.
Was this 2003? The 2003 East Coast
one of
blackout?
them. That's one
Okay,
of them.
because I was there for that.
Okay.
I was a little kid when that happened, and my dad has this wild story about being in New York City when the power went out overnight and he couldn't come home because he got stranded. But he had a great time because I shouldn't go into it too much, but the short version is that all the restaurants, suddenly their refrigerators didn't work. And
Fire sale.
so they had a fire sale, and
That's awesome.
it's 2003, so credit cards are getting really popular, but they weren't completely ubiquitous at the time. And so my dad, for some reason, was always paranoid and always just had like hundreds of dollars in his pocket. My God, you could rob that guy. I don't know why he did this, but he argued that it was because one time in New York City, the power went out and he was the only one who was able to get food for everyone in his office because he was the only person with cash.
That's awesome.
And he always used to yell at me for not having any cash in my purse. And I'm like, Dad, I don't.
Well, I have to give credit where credit is due. The cool thing about that is he has learned something about resilience, where you don't put all your eggs in a credit card shaped basket.
Yeah.
Right. So
No, you just put all of your cash in your pocket.
yeah, and then if
And
somebody
then hope
knows,
that nobody robs you in that one pocket.
so what you need to do is take $100 bills and weave it into hidden pockets throughout all of your clothing.
That would have been smarter. No,
Yeah.
but that was not.
Yeah, yeah. So.
He was obsessed with that. Oh my gosh. But that always made me giggle when you were talking about like these radial networks. In Connecticut in particular, just always had outages every summer, every time it freaking rained. It was just,
Yeah.
so I totally resonate with this.
The other thing is, part of the reason why the grid is as unreliable and expensive as it is because all of the power is above our head. They have to build these big, expensive
Right.
towers. They have to buy and maintain all of this real estate
Yeah.
at the side of the road and at the side of the railroads. And as you mentioned before, there are these things called lightning strikes, wildfires in California, hurricanes, tornadoes,
Derechos.
you have copper rustlers, you have copper thieves.
Oh yeah, people who just steal copper from places.
Yeah, because the price of copper spiked because of various issues.
Casual.
Supply chain issues, among others, tariffs. But the bottom line is, because copper is so darn expensive, it creates a very alluring target for thieves.
Yeah.
And so if it's just on a pole or on a tower,
Yep.
it's so enticing. If you bury it, it's very difficult for people to steal.
Yeah.
Or at least it creates a fairly...
It makes it a little bit more obvious if you are engraved in it.
you got to be really committed at that point. Or you got to have Billy Bob and his backhoe.
Yeah, that's true. All right. Well, one issue I do want to address before we start talking about Crucible Energy, and I promise... Oh, I had the mic. One issue that I do want to address before we move on, and I do want to talk about Crucible Energy. I promise we will get there.
Oh, good.
We will talk about what you're working on. But one thing that I didn't know until I think talking to you earlier this week, I think I had heard some things about it, but not in a lot of detail, is how is it most of them, or is it a quarter of the solar and wind projects in the US or maybe elsewhere aren't actually connected to our larger grid systems?
It's so much worse than that.
Oh, no.
Yeah.
Tell me more.
To give you some perspective, the total size of the US power grid is about 1.2 terawatts.
Okay.
Okay. There are over 12,000 renewable and storage projects in the AC grid queue.
In the queue, in line.
They're in line, and they've had to plunk down not a small amount of money to get there and to stay there. And they're being told, oh, you get to wait 4 to 10 years to connect to the grid. Oh, but wait, it gets better. Because if you add up the amount of power that they could be contributing to our grid, it amounts to about 3 terawatts. 3 terawatts is over, if you're keeping score at home, over double the amount of power that we currently use today with our grid. And here's the sucky thing. If we could, if I had a glove of Thanos and I could snap my fingers and magically connect all of those to our AC grid today,
right,
it would melt down the grid because it couldn't keep up with an extra 3 terawatts of power.
So both, it would, did you say double the size or quadruple the size?
I mean, 1.2 divided by 3.
Sorry.
I mean, that's okay. I'm
math. I can't math while podcasting.
Let's reverse that. I'm going on like 2 hours of sleep here. So it's at that measurement, it's like 2.5 times.
2.5 times. So it's 2.5 times what is
more power is in line to be connected to the grid.
And is not in the grid than is in the grid.
Correct.
Okay. Wild.
It gets even worse.
And you can't connect it because if you do connect it, it would break the grid because it'd be too much energy.
Yeah. So the queue, the AC grid queue that we were talking about, it exists in part because every time you add or remove anything to the existing AC grid, they have to do a study. It's a grid connection study because AC is antiquated AF.
Right.
Right. And so they have to do a study to figure out what needs to change so things don't completely melt down. Just because imagine if
for every single set of solar or wind panels, they have to do a study.
That's why it takes so long.
Holy cow.
It would be like if you wanted to connect a USB printer to your computer and somebody said, hold on, you got to file forms in triplicate and post it on the Vogon Homeworld. And then you have to wait, a few months before you can get approval to connect the USB cable. And then you have to hire a specific contractor so that they can plug in that USB cable for you. Is it any wonder why we have a 57% shortfall of the amount of transmission that we need? We can't grow quickly enough.
Yeah.
And we're not making more real estate because we don't have additional rights of way.
This is crazy.
It is. That's why when I think about it, doing the same thing over and over again and expecting a different result.
It's insanity.
Yeah, pretty much.
Yep.
So we need to fundamentally reevaluate how we're doing things. And my approach, if you don't mind me,
I think we can do this. I think we can talk about Crucible Energy now.
I want to
still
explain
have
how
more
I
questions.
look at it. You know?
Yeah. Here. Okay. Let's do this. Here. You just go. I don't even need to ask you. Listen. Just rock and roll.
We have a system that was designed and built over 100 years ago, and we have never gone back to the drawing board and said, there's a far better way to do things. Especially if we start with the assumption that 100-year-old technology does not need necessarily to be given a guaranteed, infinite lifespan, right? So if you can start to challenge all the assumptions,
right,
and instead you start with instead of looking back at the grid and going, why did they do it that way? Just start with a clean slate and say, okay, if we were to build a brand new system from scratch today using today's, like the best of the best of the best of today's technologies,
right,
what would we do?
Yeah.
And that's for the last 10 years, that's what I've been working on.
Yeah.
Is borrowing these ideas like from the internet, because it's been around a little while.
The internet?
We've solved one or two problems on how to move data around. And when you start to think of it more like a data network, and you are starting to use more modern technologies, you can move power around a network. Note, I didn't say the grid, I said a network.
Right.
And if you go over to China, they don't talk about a grid, they talk about a power network.
Interesting.
And that's the kind of language that I use, because I'm looking at building a superconducting mesh network for power and data with integrated storage. And when you do that, a lot of things change.
Yeah.
And a lot of things that are a kind of a headache or a nightmare or an impossibility today become very, very practical and very actually affordable. And yeah.
Well, let's dive into these superconducting mesh supergrids. I think the first thing that we need to talk about when we're talking about what you're building at Crucible Energy, we have to compare and contrast AC, alternating current, our favorite topic.
Yep.
Which are the copper wires that we all see in our neighborhoods on poles. All right. With DC, which is, what is DC
Direct
again?
current.
Direct current. So can you explain what direct current is real fast? Can you do it in a sentence? I'll give you a whole $1 if you do it in a sentence.
I'm sorry. It's easier to explain how alternating current basically propagates a wave, and it's the wave that actually carries.
Well, it's different. I guess the first thing is it's different materials. So instead of using copper, no.
Well, okay. What you're talking about is the distinction or the differentiation between superconducting versus non-superconducting.
Oh, okay. Well, then you just discuss what DC is, and ignore me and my.
So DC, direct current, can use exactly the same materials, same cables. Typically, they're configured with 2 conductors rather than 3, right? Because I explained earlier how with alternating current, because it is a waveform that travels over the wire, if you have 3 conductors and then you shift the wave by 120 degrees, 3 of them, if you have a wave, it makes a cycle of 360 degrees, 120 degrees, 240, 360. You basically balance the current across all of those. The different waveforms balance each other.
So if there's a surge in one, it can take it, but it goes down in the other.
No,
ignore me.
No, actually, okay, yeah. So the wave, as it's going up on one, is going down equally on another.
Okay.
But it's like two going down balance the amount of one going up, and vice versa. It's
So is this more like perhaps the moon and tides? So so tides happen because the water gravitates towards the moon, and the moon travels across the earth throughout the day. And so like basically the water is high tide, like it goes up because it's trying to stretch and reach the moon. So on one side of the earth closest to the moon, it's going up, and on the other side it's going down. Yeah? I think it might be a good comparison. Did I do it? No? Or are they going up on both sides?
No, I mean, your description for how and why tides work the way they do, beautiful. I love it. I don't think that is helping people to understand the difference between AC and DC.
This is why I got to stop talking, guys.
No, it's all
I'm
good.
supposed to be good at translating jargon.
That was a beautiful description
was a
of
beautiful
microgravitational influence between the moon.
We love
and
gravitational
water.
pulls.
Yes, it's beautiful.
Listen.
Beautiful. So
Just elegant.
the bottom line is direct current is simpler, easier to work with, but if you are not careful and you're dealing with, let's say, high voltage
Right.
DC, you can vaporize body parts or entire people.
I heard something about, was it Einstein and elephants? I was told don't look at photos.
Okay. Well, I can tell you
Right.
part of the reason why we have AC for our power transmission today is because of a rivalry between Tesla and Edison. And if you recall, the electric chair was invented not by Tesla but by Edison in order to show people how dangerous DC current is.
Interesting. So DC was Tesla's invention.
DC, yes.
Yeah, it was like Tesla's thing, and Edison was trying to show off how dangerous it was. And he was he was more of a really vicious businessman marketer type,
Yeah.
in addition to the inventor stuff.
Well, in fact, Tesla worked in Edison's lab.
Right.
And he invented a number of things that Edison commercialized. And so I think it's probably incorrect to say that Tesla invented DC.
Okay.
But he invented a lot of early breakthroughs that made it feasible to work with it
Makes
and
sense.
useful. But I think it reminds me of disinformation campaigns today on social media.
Misinformation station.
Exactly. So it seems the thing is, you had somebody who was opposed to DC invent a device specifically to illustrate the worst possible outcome. But here's the thing: it's possible to design DC transmission grids that are much safer than AC grids. And the way that I'm doing it is with medium voltage, not high voltage. The other thing is, I'm not putting it up above your head on a pole or on a tower where a lightning storm can cause those down wires, or a hurricane or a tornado or a wildfire. You don't have to worry about fallen power lines if you underground your transmission.
And so you showed me a visual
Yeah.
that I'm going to have come up on the screen here.
Sure.
That kind of shows the difference between what the infrastructure looks like when it comes to AC systems now,
Yep.
and what Crucible Energy is proposing here,
Right.
and building and whatnot, right? And so on the AC end of things, you guys have probably, I'm going to describe them out loud, but in case you're listening and not watching, but AC systems are like the power lines that you see everywhere. But the largest ones, the ones that transport the most amount of energy, are these huge behemoths that you've seen. How many lines do they have on either side? It's kind of like they're these big metal things with the big arms.
Yeah. So they'll sometimes have 3 conductors at the minimum, because
Right.
AC requires 3 conductors, if you
Yeah.
recall. Sometimes they'll actually have 3 of them spaced vertically on let's say the left side and 3 spaced vertically on the right side. And so you've basically got 2 lanes
Yeah.
of power transmission with one tower. And they're doing even more now, where they're going even taller. That's more expensive. It's more, potential sources of failure. So yeah, it's a nightmare.
Yeah. Well, I'll have you know that when I was a little girl, your nightmare of these giant AC power grids were my favorite thing to look at while driving.
Oh, really?
So I don't know if you've seen the ones off of like 494 on the way to like Minnetonka for any of
Yeah.
us locals here. So you know how some of them were, they kind of look like this, and then some of them they look like that, and some of them like they go like this, whatever.
Yeah.
Well, as a little kid, I used to say they were the dancing power lines.
That's awesome. Because if you
Because they
fix
looked
your
like
eye-
they were dancing. They
Oh,
looked
yeah.
like people that they were dancing with their arms.
Oh yeah, because it would be like a what is it? What's the term where you have the different pictures and a little slot and you turn it?
Oh, yeah.
It's not a rotoscope. It's what I'm talking about.
I know what you're
A
talking about. It was like
cinescope.
very early animation, basically.
Exactly.
Yeah.
Exactly. And you could have a series of like Edward Muybridge photos
Yeah.
of like a galloping horse
Yeah.
or whatever.
And I was a big animation nerd as a little kid. And so I saw the dancing power lines, and my parents thought that was the funniest thing.
That's awesome.
And it's one of their favorite stories that they talk about with me. And so when you showed me that slide, I did everything I could to not blurt that out because I wanted to get your reaction on camera anyway. So we've got these big systems that
broken
look like
robot.
this, that dance. And then we've got smaller systems that are like the X and the T kind of shaped things that we're probably used to seeing in our neighborhoods.
Right.
But what you're proposing is different.
Yes.
So it sounded like we've got cables. Yes, is the correct terminology. Tubes.
Yeah, they're superconducting
Yes.
transmission cables, right?
And you said how many inches wide?
Well, just to give you kind of an idea, so the cable itself could be, let's say, 6.5 inches in diameter,
Okay.
circa.
Something like this? Yeah.
Yep. And it can carry up to, theoretically, it could carry up to about 15 gigawatts of power. So that's
Yeah.
like,
And you said the old ones carry 3? The big giant ones carry 3 gigawatts?
no, the big ones, typically those are about 2 gigawatts.
Oh, 2. Sorry.
Yeah.
Yeah.
So, I mean, ultimately, we're talking about
So you're
many times. I mean, theoretically, and here's the other thing: you have to hold those on the broken robot. You have to separate those conductors by a distance. Otherwise, they'll melt their neighboring cables.
Yeah, but these ones you don't need to.
Right.
So
So the beauty of it is you don't have to have 100 meters or 85 meters of right of way, because you can have one or more superconducting cables buried underground.
right.
And what we're using is 100% trenchless, meaning we're not disrupting the earth except for to drill a hole on one side. And then we've got a robot that drills the whole way, and then it comes up on the other end.
So this is more like when they install like fiber, if you're getting fiber internet into your house, than it is if you're, say, putting in new plumbing systems. Maybe?
Yeah.
Yeah.
Well, I mean, it's more like fiber optic versus coaxial cable, because coaxial cable can only carry so much. But then you
Right.
move over to fiber optic and you can carry,
Well, I meant you don't need trenches.
Gotcha. Yeah, sorry. Yeah, we're talking about above ground versus below ground. And so
Yeah.
I misstated that. Really, I mean, you can actually go, theoretically, you could go up to about 30 gigawatts. You'd have to maybe scale up the cable a little bit, but I'm designing next generation cables that can carry 15 and 30 gigawatts. The point is, because you don't have to put it up on a tower and you don't have to worry about what's called thermal backfill, which is when you bury a cable, you have to worry about it heating up even more. So you use the ground to cool it down.
Right.
And so you can't put 2 of those cables right by each other. And this is why in the world of high voltage AC, or even high voltage DC, if you try and bury those cables, you get to add zeros to the end of the price tag, because it's much more expensive to bury that type of technology, which is why everybody does it above your head.
And then
right?
you said also that these cables, do they also contain the liquid nitrogen?
Yep.
Okay. So can you explain these closed loop systems for us really quick?
So I should probably explain, why are we talking about superconducting cables in the first place?
True.
The major advantage is you can move massive amounts of power.
Yeah. 15 instead of 2 gigawatts.
You can scale up from there. I mean, you can move theoretically hundreds of gigawatts in a 1 meter right of way underground.
Right.
That's if you get to like hundreds of gigawatts, you're talking about the amount of power that entire continents use.
Right.
Right. So this is not a small amount of power, but you can fit it into a tiny little, 1 meter right of way, and you can do it entirely underground. And ultimately, the cool thing about superconductivity is you can move massive amounts of power, and it produces zero losses regardless of distance. Or I should say effectively zero. I mean, it's a rounding error. It's like such a minuscule amount that is lost that for all intents and purposes, we can say lossless.
Yeah. Compared to, we were talking about 10% earlier, right?
Yes.
But then there's peakers, which is separate.
Oh, yeah. So let's talk about peaker plants for a second, if you don't mind.
Okay, quick.
Yeah.
Concise.
So, but just to put it in perspective, so the losses that are built into our AC transmission system losses are about 10% in the US, 16% in the EU, and over 30% in developing regions of the world.
Right.
So on top of that, you were talking about peaker plants. Yes. So our system, as we talked about earlier, doesn't handle variability very well.
Right.
Right. And so you have what's called a base load power, which means they're always generating the amount of power that most people use most of the time. Right. And that means that on a hot summer day and everybody turns on their AC and there's not enough power, you might see the demand go through the roof, and it blows past anything that the base load power that the grid is designed to handle can cope with. So they have what's called a peaker plant, or many peaker plants. And what these do is they are always running. They're always burning fuel, fossil fuels, just in case there's a peak of demand, so that they can very quickly respond. It's called spinning reserve. But the reason they have to do that is because these are such massive machines. It actually can take hours or even days for them to go from off to all the way on.
So we basically have these systems that are generating a lot of power, spending a lot of energy to create that power.
And pollution as well.
And pollution, that are always on just in case demand goes up.
Right. And outpaces the base load generation to be able to satisfy everybody's needs.
Yeah, which is probably very inefficient, because we probably don't need that amount of power 24/7.
Exactly. So what it looks like is, so first of all, these are the dirtiest parts of the grid. We're talking about 50%, like half of the carbon footprint of the entire grid around the world comes down to peaker plants. They are the culprit. And here's what really adds insult to injury. Even though they're contributing half of our carbon footprint, they're only delivering 5% of the power that's actually used.
Wait, hang on. Say that one more time.
They're generating power and pollution 24/7, 365. They generate half of the carbon footprint of our power grid, and yet they only deliver 5% of the power actually used.
What?
It's that inefficient.
I love how you told me all this on Monday, and I only comprehended like half of it. and now I keep having real reactions, even though you told me this 5 days ago.
Sometimes it takes a little while for the magnitude and the impact to sink in.
That is crazy. Why is this insane?
Well, exactly. And this is where I'm like, look, if we were to try to design a system like we did today, like we have today, people would be like, are you crazy? Why
Right.
would somebody intentionally design a system this inefficient, this sucky?
This bad. Yeah.
And the answer is they didn't know any better, or they didn't have
Yeah.
it was not really feasible, but for Edison's skull effery.
Edison, damn you,
Yeah,
Edison.
he was not a nice guy at
We
times.
support Nikola Tesla, but not necessarily Tesla vehicle. Well, no.
All good. So yeah, it's really incredibly inefficient, and so a lot of people have been talking about this for a while, and I've realized that it is possible using a type of storage, one or more types of storage, to actually replace the need for peaker plants, and it will cost significantly less. I'm actually looking at buying peaker plants and buying them just so that I can shut them down.
Oh,
But wait,
wait, there's more.
there's more. Because once I buy them, I can install my own hybrid energy storage on the spot.
Yeah.
And it's a combination of batteries and a number of other faster storage that can respond in millionths of a second.
Yeah.
So it can respond even faster than the peaker plant could,
Yes.
which means that it can keep the power supply much more stable and
Right.
within the Goldilocks zone that we were talking about earlier.
Right.
So if you can keep the power on the AC side within its Goldilocks zone, 24/7, 365, you don't have multi-million-dollar components going up in flames or
Right.
bursting into sparks because it's got way too much power, or
Right.
because there's massive flickering and transients and stuff like that. So I guess where I'm going with that is if you add the right amount of storage in enough places, we could literally turn off every peaker plant in the world, and we would cut our carbon footprint of the electrical grid in half.
Wow.
And so the beauty of this, and in the process, you would make power cheaper and more reliable.
Yeah.
It becomes a complete no-brainer once you do the math and realize, oh, these things are connected.
Yeah. But getting across the finish line, so this to me is like where I'm like, how are you going to pull this off? And so I think I'm going to jump ahead to a question. We can go back if we want later, but I want to jump ahead to regulation because so one of the biggest problems in revolutionizing this industry is a mix of large incumbents who dominate the space and government regulation, which makes it really, really challenging to revitalize our energy grid or make these big changes. And then on top of that, then you have if you need public feedback or something like that. I have a dear aunt who I'm sure is watching this. Hi, Aunt Ellen, who is an activist for clean energy and with a strong focus on water. And so I know this is something that she's particularly passionate about and often protests things that potentially coming in.
Yeah.
So I'm curious, how is your team navigating that landscape? Because from my perspective, that seems to be the biggest hurdle is like you have some incredible products that could be really, really cool.
Yeah.
There is a ton of money in the space, which makes it seem more viable. But where I get nervous is can you execute? And specifically, like, is this regulation competition mix going to be a major barrier, or are there ways that you can design a solution that are different? This is something we talked about, and I would love to hear what you have to say.
Yeah. I love this question because most people are used to thinking in terms of how things have been done.
Right.
And so they look at the overhead power lines and go, oh, well, if I want to add power, I have to do it overhead.
Yeah.
I have to use high voltage because if I use anything other than high voltage, my resistive line losses actually go up. So that 10% reactive losses would go much higher if they didn't use high voltage. So whenever you're working with something that's not superconductive, that means that high voltage is almost a prerequisite. It's the way that we prevent all of our power from getting lost along the way. Bottom line is, everybody's used to thinking you have to use certain approaches, but the beauty of that is, let's say FERC, the Federal Energy Regulatory Commission, I think is
Yes.
that,
Nailed it.
FERC.
FERC.
FERC has a certain purview. They regulate high voltage. They regulate AC. And they also regulate interstate, meaning between state connections.
But you're not doing high voltage.
We're using medium voltage, not high voltage. We're using direct current, not alternating current. And also, we can decide when and where we cross state boundaries.
Right.
And if we have, let's say, cooperation from the parties who would like a more resilient grid and would like their power cost to actually go down, we can connect to the AC grid. And wherever we touch the AC grid, we make it more resilient and we make power costs go down.
Yeah.
And the beauty of this is, though, we don't have to ask permission in a lot of cases. And when we do have to ask for permission, it's typically at the state and local level. And the conversation is really simple. It's like, well, are you going to tear up the side of the road? Are you going to dig a trench? Nope. We're going to drill a hole, like 6-inch hole.
Again, 6 inches. Like that basketball, for anybody watching on that camera, that basketball is larger than this cable.
Yeah.
Yeah.
Yeah. So it's a hole. You're drilling one hole, and then it's called horizontal directional drilling, or HDD. And this is technology that the oil and gas industry pioneered, and they have deep experience in it. And that's the other thing we were talking about, aligning incentives. A lot of people, when it comes to incumbent industries, are threatened that you're going to take their cookie.
Right.
Right.
But you're saying oil and gas invented this tech.
They did. And I want to partner with them and then show them a more profitable revenue stream and way of in fact, several revenue streams that actually lower their risk compared to what they're used to and actually give them much higher returns. So I want to work with the oil and gas industry. And also, this is the other cool thing. Oil and gas industry actually has a ton of disused pipelines all around the world.
Right.
And as it turns out,
Old pipelines that just went out of date, people stopped using them for whatever reason. Yeah.
and or it would have required a lot of maintenance and upgrades. And at a certain point, the juice just wasn't worth the squeeze. It's kind of like when you have a junker and the transmission blows, and it makes more sense to just trade it in and get a...
Your car is totaled even if it's only broken on the front left-hand side.
Exactly. It's juice isn't worth the squeeze, right? So in that situation, you've got all of these pipelines that are not being used, and we can deploy, because they're so tiny, we can deploy our high temperature superconducting transmission cables inside existing power, existing disused oil and gas pipelines. And the beauty of that is we can drive down the cost of deployment and the time necessary to deploy by 75%.
All right. I've got like two different categories of questions for you, but I think I'm going to start with the first one and hope that I remember the second one later.
Right.
But the first one is, so it seems like you found a magical loophole, which is great. For business, okay?
Several.
You found several loopholes. You're building DC, you're not building AC. You're building in medium voltage, you're not building in high voltage. You can avoid building these lines interstate and just have them be in single states at a time, unless you decide you're going to wait for that investment to get confirmation from local governments to do this. Well, my question is, and then you can interrupt all you want. Okay. But my question is, because I know the reason that you're doing this is because you are trying to do everything you can to fight against climate change and build more efficient systems and do things better.
Yeah.
But a lot of the reason that these regulations are in here, and I think what a lot of people think of when they think about regulations, especially if you're thinking like my Aunt Ellen, my absolute dream of an aunt, is focused on is figuring out how do we keep companies ethical and doing the right things. So my question is, if you are finding these loopholes, how are you, I guess, regulating yourselves or making sure that you're making the right decisions
Yeah.
to not cause unintended harm or consequences?
Yeah. I love that question. Thank you. So yeah, I haven't really articulated this yet, but part of the reason why I started this company is I actually am trying to figure out how to address the biggest problems with our energy system so that we can get to net zero, meaning we're not making the ocean and the atmosphere any worse than it already is. And if we're doing, emissions, let's say in one place, we are eliminating or reversing those emissions elsewhere within the system, and it balances out. That's why they call it net zero. I'm working to drive down the cost of energy because the cost of energy, power, electricity, is a rate limiting step for our ability to deeply decarbonize our economy.
Right.
The thing that makes the difference between whether it is possible to add more solar, wind, storage, geothermal, fully sustainable power is the grid, because you're generating all of these electrons, sustainable electrons. And here's the sucky thing. We have all of this renewable power. I think I could be wrong, but I think it's about 64% of the mix of the grid right now is renewables. But 30% of that is actually being thrown away. The industry calls it curtailment. I call it leaving money on the table. I also call it incredibly inefficient. It's like taking a giant pile of money and just putting lighter fluid on it and setting fire to it, we have more sustainable energy, about 30% more energy that's sustainable that we could be using, but for the congested grid. And so the idea is to massively upgrade the transmission capacity of our power system so that we can move those electrons anywhere, regardless of distance, without losing them. And we never have to throw away any sustainable energy that is generated, because we can either transmit it, we can use it, we can store it. We have all kinds of flexibility that we don't have with the current system.
Right.
So the bottom line is, I'm designing the architecture of the system, and I'm building my company based on sustainable practices.
Right.
Because don't get me wrong, when people talk about regulations, they usually think of it as a bad thing. I actually think that regulations are a good thing most of the time, because they're designed to protect people and companies and create a level playing field and make sure that one company cannot, let's say, pollute a river and harm everybody downstream from that and poison them. So like they're able to skip costs on certain things. And what they're doing is they're shifting those costs to everybody else.
Yeah.
Right. It's they're called externalities. Right. And the Europeans have been pretty good about trying to figure out how and why different companies try to shift the burden of paying for things to somebody else.
Right.
And if you emit, let's say, carbon or greenhouse gases into the atmosphere, you're shifting the burden of cleaning up those emissions to our kids and to everybody else in the world. And so the idea is to create a happy path or a simpler system that is more profitable, more reliable, and basically more affordable for everybody, so that it's easier to do the right thing for sustainability and for society. So you don't ask people to fight against human nature. People are I'm sorry, people, I love people, but they're fundamentally lazy. Okay. Just to put this into perspective that, people from the online audience might understand. It's like there's a statistic that 90% of the people who go to a website never even scroll down.
Right.
They'll look at it and go, I don't want this, and they'll leave. That's called the bailout rate. So 90% of the people who go to a website are too lazy to even scroll down to see what else is on the page. And that's okay. They can do that. But it also speaks to how people are incredibly lazy. And if you give them two paths, one's harder, one's easier, and they seem roughly the same, they'll choose the easier path.
Right.
So what I'm trying to do is figure out an easy path for everybody to be able to do the right thing for the environment and for sustainability and not shift costs, environmental costs, to other people or to our kids. And if you align enough of those incentives in the right direction, it kind of becomes harder for people to do the wrong thing and harder for people to create those unintended consequences. Because I'm building into this architecture and in the way that I'm operating my business, I'm building structural safeguards so that if somebody wanted to do something, emitting more pollution, for example, or whatever, it might have all the right intentions. It's like, oh, well, we can't get a hold of solar quickly enough, or, oh, we can't get connected to the grid. We bought the panels and we built them. We have a solar farm. All of our money is sunk into it, but we can't get to the power because the grid is too congested.
Right.
So what if you didn't have to worry about that? What if literally, if any sustainable project that you wanted to build, you could build it 10 times faster, or at least you could get it connected to an off-taker. You would get to revenue 10 times faster. So what we're doing is we're building this stuff out in 6 to 9 months instead of 4 to 10 years.
Yeah.
If you do the math, that's literally 10 times faster. And so we're also working on the financial obstacles so that people can afford to build more solar, more wind, more supercritical CO2, geothermal. All of these things. We're trying to make it so that the options that are better for sustainability and for the environment are the cheaper, more affordable, more reliable, better features. What would you call that? Basically, they have all the things that people are looking for, and then they compare. It's kind of like, did you ever see Malcolm X?
No.
It's a brilliant, brilliant movie.
I know. I've heard great things about it. I just
Early
haven't seen
Denzel
it.
Washington. So his mentor, Elijah Muhammad, talked about, if you take, he created he poured 2 glasses of water side by side. He said, if you pour ink into this and foul the water, and people don't have another option, they'll drink, they won't like it, but they'll drink this fouled water. But if you give them
the option and there's no reason not to choose the clean water, they'll choose the clean water every single time. I think of it that way. If you could buy an EV and the EV cost the same or less than a gas car, and if it had, let's say, twice the range, the same or even twice the range of a gas car, and you could charge it from empty to full in half the time that it takes for people to fill their gas tank at the gas station, I don't think you'd have a single person who'd say, "Oh yeah, I want a truck. Yeah,
I got to have a Hemi."
Yeah. There might be some people, but that's more of a political, personality-driven decision rather than maybe the smart one.
Yeah.
perhaps.
And if somebody wants to spend more money and have to
True.
drive to a gas station in order to fuel
Instead of
up-
just fueling at home. Yeah.
yeah, instead of just pulling into their garage. Yeah, I mean, I think of it in terms of creating a happy path and making the the options that are best for society and best for the sustainability of our power grid and of our economy in general, make it more profitable, make it so that all of the objections that people traditionally have disappear. So like, for example, you were talking about AI data centers and water. There are a lot of people who are used to think, I've heard people say, oh, well, I'm afraid to use ChatGPT because I've heard every time I type in a question to ChatGPT, it evaporates a gallon of drinkable water.
Yeah.
Well, you have that because data centers are fundamentally inefficient. They're generating all this waste heat, and then they have to expend additional power in order to cool it. And so they'll use water, they'll evaporate it to cool things down. Well, if you make the data center like several times more efficient and you eliminate those inefficiencies, you don't have to evaporate water in order to cool it down. And then more importantly, if you build a net zero data center, instead of consuming water, you can actually make it so that it generates more drinkable water than it consumes. So now if you have a net zero data center that generates more drinkable water than it consumes, how many protests do you think you would have? Not very many.
Right.
So now take it one step further. What if we could take CO2 and methane and other greenhouse gases out of the atmosphere and use an electrochemical reaction to convert that into graphene, carbon black, carbon nanotubes. These are expensive, valuable materials because we can't get enough of it.
Yeah.
And guess what? It's in the air. Like every time somebody
now.
farts, they're emitting methane into
And
the air.
if you just happen to have purchased all of these peaker plants.
Exactly. So the emissions that are in the air and the carbon that's in the air, we can, if we drive down the cost of power sufficiently, we can make it economical and even profitable to reverse climate change in our lifetimes. So, and that's what gets me excited is because that's the rate limiting step. If we can draw the carbon and the methane and greenhouse gases out of the atmosphere at a fast enough rate, we can reverse climate change. We can get to net zero faster, and we can actually reverse all of the damage that's been done since the industrial age, since we figured out how to rub two sticks together and create a fire. We can reverse our atmosphere back to pre-industrial levels of greenhouse gases. We can even reverse ocean acidification to pre-industrial levels. And we've just hit a tipping point within the last couple weeks.
Yeah.
You might have heard it in the news. They're talking about this as, okay, we have crossed a threshold that we don't know how we're going to get back.
Right.
Like shit is getting real. Okay. So it's not enough for us to not damage the environment at the rate that we were before. Right. So I feel like this transition over decades and centuries, and people are talking, maybe we can slow down our emissions and maybe achieve net zero in the next 50 to 75 to 100 years, but it's actually costing us trillions, tens of trillions of dollars a year. I think one study I read is about 36 trillion a year. It costs us every year that we don't get to net zero.
Yeah.
Well, if we're talking about 50, 75, 100 years, let's call it 100 years. And every year that we wait, it becomes more expensive.
Right.
So a few years ago, it was only 25, a paltry 25 trillion. And since then, in the last few years, it's grown from 25 to 36 trillion. So the point is that if you've got an expense,
Yeah.
let's pretend you have like massive credit card debt and you're paying like 30% APR on it, right? And you've maxed out your credit cards, and then you've got a home loan at 3 or 4%. You're making your home loan payments, but then your credit card continues to rack up all this debt every month, and it creates a strain on your budget, right? It's a massive drain in your resources. So if you could take that and instead make your credit cards go bye-bye, or do you accelerate the rate at which you pay them down, it frees up all kinds of more money.
Yeah.
So what I'm talking about doing is making it not just economical, but profitable.
Right. Make it so that this is the desirable thing to do.
Right.
Instead of just the feel-good thing to do.
Right. So the important thing is, with massive amounts of power, and more importantly, sustainable power, you can not just economically, but profitably draw carbon and greenhouse gases out of the atmosphere and produce these incredibly profitable products called graphene, carbon black, carbon nanotubes. And you can put it into either in a deep well, and it basically remineralizes, and it becomes permanent sequestration, right? Or you can actually add it to concrete. And this is another initiative that I'm working
concrete. I know. You've got so many initiatives. All right.
But the bottom line is, every time you build a data center, they use more concrete than any other sector of the economy. If you can make that concrete so that it includes graphene and carbon black, you can actually permanently sequester the carbon. And instead of having a net zero data center, you actually have a carbon negative data center. So every time you build that, or anything out of concrete. So we take the dirtiest part of our economy and we make it the cleanest.
Yeah. All right. Sam,
I'm so sorry.
It's all right. It's all so fascinating, but also we are so out of time.
Okay.
So, if there is one more thing that you could share with this audience today,
Okay.
what is the last thing you would like to share with everybody before wrapping up here? And I need it to be under 10 minutes.
Okay. Well, we should probably talk about how this relates to AI.
Yeah.
We've been talking about AI data centers, but we really haven't been talking about what we're doing with AI.
Go for it.
Except for building
Go fast.
more efficient AI data centers. So in the last few years, I've been working with some fairly cutting edge AI. So I was working at Hewlett Packard Enterprise, HPE, and I got really, really frustrated at things that would break because there was no way of knowing unintended consequences. You'd make a change here and it would have a ripple effect throughout complex software. And so what I decided to do is create a system that would automatically, deterministically map out all of the behavior of any software system, and it would produce a set of tests to fully document all of that behavior, and then it creates a digital twin for the software system, and then you can use that to refactor a drop-in replacement and guaranteed backward compatibility. Oh yeah, and you also have full documentation, but you can refactor into any other language. So you could have an old RPG or COBOL or Fortran or whatever, and you could refactor it into a memory-safe language like Rust. Or if you're really into microservices, you could convert it into Go or Java or whatever. But the point is to be able to automate that using a number of techniques. Now, in the last couple of years, I was using traditional computing approaches. In the last year or two, I've been working on an AI approach that allows us to, and of course, I'm applying this not just to software, I'm now applying this to power systems. So I'm creating what's called a multi-agent reinforcement learning system because our network, our mesh network actually has blockchain integrated smart sensors everywhere. And so what this does is it gives our power system a nervous system, and the brain of it is it's like the gray matter
So instead of the subway system that we described earlier,
right.
of a subway having to hit a piece of metal so that a light can go off in a room where hopefully somebody has noticed it,
Right.
And can say that's where the subway is. You can use these types of sensors to say, we need more power in this part of the grid. We need less power in this part of the grid. How can we redirect our resources to be more responsive?
Yeah, it goes beyond that. So, if you bump your shin into a coffee table, a signal doesn't have to go all the way to your brain. There's a part of your nervous system that has a degree of intelligence that says, oh, I probably don't want to do that. Likewise, if you grab a hot pan on a stove, it doesn't have to travel all the way to your brain and back because there is distributed intelligence in your nervous system and in your spinal cord. So what I'm talking about is a self-healing, self-optimizing mesh network. So the intelligence is built into the fabric of the network. So it can dynamically reroute power and clear faults and self-heal in milliseconds rather than sending somebody out to, make changes manually.
Yeah.
So, yeah.
But I think, the most important part for me for this was I want people to be, so many of my friends are so down and so depressed and so nihilistic.
Yeah.
And a lot of these problems are solvable, but the more that we treat them like impossibilities that will never happen, the less likely we are to actually push for these things, right?
Yeah. I read a quote years ago. I think it was okay. It's
Brain died.
Guy used to run, I think, MIT's media lab. And so what he said is basically, it's if you're convinced that something is impossible, you pretty much have helped to guarantee that is the truth. But if you have the belief that something is possible, then it takes it out of the realm of the impossible and it brings it into, again, I'm using way too many words. I want to find the quote because what it means is that if you can see a way that a better world is possible, then a lot more people are willing to work toward that goal. But if you convince everybody that is not even possible, or if people convince themselves and each other that is not possible, that everybody has to stop having babies, everybody has to stop driving. You can't use ChatGPT because it's going to evaporate all our water. If you are all convinced, if people are all convinced that there is no better way, I understand why a lot of people for the last couple generations are like, oh man, this sucks.
Right.
I'm not better off than my parents are. People are living at home with their parents, or in some cases they're dealing with way more college debt, student loan debt than previous generations. All of these things make it so that people get frustrated and they tend to
poking at like everything that's wrong, right? Like
exactly.
They're digging themselves into a hole and digging the rest of us with us. And like on one hand, I think it's important to be critical and important to look at the problems and to not just hype everything up. Like a lot of like the AI hype machine right now is kind of driving me crazy.
Right.
But the like alternative of everything sucks and we're never going to find any solutions. God, that's like a one-way ticket to never getting anything done.
Yeah. I mean, it's interesting because, and not that social media is a good place for nuance or civil conversations, but
we are always nuanced and civil here at Swift Start Go.
So people are talking about, oh, well, AI data centers, they're causing the world to melt down. We have to all stop using AI.
Right.
Yeah, like that's going to happen.
Yeah.
Seriously. So, I mean, I chimed in. I'm like, there's an alternative. If you make the power that you're delivering to the data center fully sustainable,
Yeah.
if you make it so the data center is net zero or carbon negative, if you make it so that it generates more drinkable water than it consumes, what's not to like?
Yeah. I mean, there's some things in life where there isn't another option. There isn't a way to make things better. And then there are other times where there are ways to make things better. And so that's why I wanted to have you on the show. Well, Sam, it has been such a blast chatting with you. As you know, I could chat with you all day long.
Likewise.
About this. I could have you on the show all day long if I could, but alas, we have to get out of here because I think Nate needs to go home.
Okay.
So anyways, thank you to Nate and the Upload Company for hosting us. Sorry, Nate, that we kept you for so long. But Sam, if people want to learn more about you or Crucible Energy, or maybe want to reach out for a potential partnership, how can they get a hold of you?
I would go to crucible.energy. Or
amazing.
Or if that's if you're one of those people that thinks that everything has to end with .com, you could just go to crucibleenergy.com.
You've got both?
We do.
Oh my gosh, that's amazing. Listen, crucible.energy or crucibleenergy.com, whichever one you decide to choose. Amazing. But thank you, Sam, so much for being here today. I hope you had just as much fun as I did.
Probably more. You had the hard part. I had the easy part.
I had to listen, and I'm bad at listening. All right. But thank you everybody for watching. In case you're new here and you haven't watched the show before, this is Swift Start Go, a show where we talk all about AI, creativity, and the future of work. And today that involved AI, energy, and climate. I'm your host, Carolyn Swift Holden, thus Swift Start Go. And if you like this show, you can like, comment, subscribe wherever you are watching or listening. And if you have questions, we talked a lot about a lot of big ideas and, frankly, an incredibly ambitious project. I've talked to a lot of founders who have built a lot of different types of things, and this is a project of gargantuan size. From my personal perspective as somebody who's, frankly, only really been in the software space. So as soon as we get into hardware, I'm like, oh my gosh. So if you have any thoughts or questions, please feel free to share them in the comments below. Sam, would you be open to answering any questions if they come up?
Yeah, happy to.
Amazing. Okay. So thank you so much again for watching, and hope you're having an absolutely fantastic day. Bye, everyone.
Hasta luego. Comes down to peaker plants. They are the culprit. And here's what really adds insult to injury. Even though they're contributing half of our carbon footprint, they're only delivering 5% of the power that's actually used.
Wait.